James Webb may have found the strongest sign of life ever detected beyond Earth. On K2-18 b, 120 light-years away, scientists detected a possible chemical signal with 99.7% confidence, and on Earth, that chemical is linked to living oceans. Before we go deeper, take 1 second to like and subscribe, because this discovery could change the search for life forever. Now, let 'em begin. That smell when you step onto the beach. Salt. Seaweed, something alive and ancient in the air, has a scientific name, dimethyl sulfide, DMS. Most people never think twice about it. It's just the ocean smell, a background detail that disappears from your awareness within minutes. But for astrobiologists, dimethyl sulfide is one of the most consequential molecules ever studied, and the reason comes down to a single, unbreakable rule about where it comes from. Not volcanoes, not storms, not any geological or atmospheric process science has ever documented. DMS is produced exclusively by living organisms, marine phytoplankton, microbial bacteria, microscopic life forms floating in the upper layers of the ocean. They consume organic matter, metabolize it, and release dimethyl sulfide as a byproduct into the air. The chain is biological from start to finish. Take away the organisms, and the molecule disappears with them. No exceptions exist. No alternative production pathway has ever been confirmed. Across every ocean basin, every climate zone, every ecosystem on Earth that has been studied, the relationship holds without deviation. A DMS means life was here. This is not a hypothesis. It is one of the most thoroughly documented chemical relationships in astrobiology. Scientists treat it as a rule so solid it functions as an axiom, a starting point, not a conclusion. No life, no DMS, period. That is the foundation. Hold it. In September 2023, a research team at the University of Cambridge published a paper in the Astrophysical Journal Letters. The subject was K2-18b, a planet 120 light-years from Earth, orbiting a dim red star in the constellation Leo. Webb had been observing it, and among the atmospheric signals the telescope returned, the data contained a reading consistent with dimethyl sulfide. The initial confidence level was 3 sigma. In scientific terms, that means the probability of the signal being random noise, a false positive, an instrument artifact, a coincidence, is roughly 0.3%. Not a confirmed detection by the standards of physics, but not something you walk away from either. The team kept watching. More transits, more data collected across multiple observation windows, more processing, cross-checking, noise elimination. By 2025, independent reanalysis of the accumulated Webb data pushed the DMS signal to 4.2 sigma. That number translates directly to a 99.7% probability that the detection is real. 99.7% on a planet 120 light-years away. If DMS only exists where life exists, then what is making DMS on K2-18b? That is not a rhetorical flourish. It is the load-bearing question at the center of the most significant astronomical finding in human history. Sitting quietly inside a set of infrared absorption readings from a telescope orbiting the Sun 1.5 million kilometers from Earth. Let that land before moving past it. To understand how Webb extracted this information at all, picture something you already know. Press your thumb against a glass pane and hold it up to a light source. What you see is a smudge-your smudge, with its own loops and ridges and patterns that have never existed on another human hand in recorded history. No 2 fingerprints are identical. Now extend that logic to chemistry. Every molecule absorbs light at specific wavelengths unique to its structure. Methane absorbs at its frequencies, carbon dioxide at its own, water vapor at another set entirely. Dimethyl sulfide has a distinct absorption signature centered around 3.3 micrometers and 9.7 micrometers in the infrared range, its fingerprint, as precise and individual as yours on that glass pane. When K2-18b passes in front of its host star, an event called a transit starlight filters through the thin atmospheric layer at the planet's edge before continuing toward Webb's mirrors. Molecules in that atmosphere intercept specific wavelengths and absorb them. What arrives at the telescope is starlight with absences carved into it, a spectrum with gaps. Webb reads those gaps. From the pattern of what's missing, it reconstructs what's present. The Cambridge team ran that reconstruction. The gaps in K2-18b's spectrum included the fingerprint of dimethyl sulfide. And now the irony arrives, and it is genuinely uncomfortable. The compound that makes you wrinkle your nose walking past a stagnant pond, the low tide smell, the harbor at noon smell, the thing you associate with rotting seaweed baking in August heat, may be the single most important molecule ever detected beyond Earth. Not a radio signal from an advanced civilization, not a megastructure orbiting a distant star. A pungent little metabolic byproduct of microbes eating lunch, floating up through an alien ocean and into an alien sky 120 light years away. The universe is telling us something enormous, and it chose the least glamorous possible messenger to say it. Set the irony aside though, because the chemistry underneath it is what matters. Dimethyl sulfide cannot form through inorganic reactions in a hydrogen-dominated atmosphere. This has been modeled extensively and rigorously. Run every known abiotic pathway, photochemical reactions driven by stellar radiation, volcanic outgassing from a geologically active interior, delivery of organic compounds via meteorite impacts, hydrothermal chemistry from seafloor vents. None of them produce DMS at concentrations high enough to generate a detectable spectroscopic signal under the atmospheric conditions Webb has characterized on K2-18 The non-biological explanations don't just fall short. They fall short by orders of magnitude. Which means that if the signal is real and 4.2 sigma says, it almost certainly is the explanation that survives after eliminating everything else is the same one that accounts for every molecule of dimethyl sulfide ever measured in Earth's atmosphere. Something alive is making it, not a theory reached by optimism. A conclusion reached by elimination, the same method that has driven every major scientific discovery, from the germ theory of disease to the detection of gravitational waves. When every alternative explanation fails, what remains is your answer. DMS on K2-18 points to one thing, and that one thing changes everything about how we understand our place in this universe. But DMS is only the first clue. What makes the planet holding it genuinely bizarre hasn't even been touched yet. 3 sigma is not enough either, not when the claim on the table is life beyond Earth. To understand why the journey from 3 sigma to 4.2 sigma matters as much as the destination itself, you need to understand what sigma actually measures. Each sigma level represents a standard deviation from what you'd expect to see by pure chance. 3 sigma means the probability of a false positive, a random fluctuation in the data mimicking a real signal, is roughly 0.3%. Sounds convincing, but in particle physics, 3 sigma results have collapsed before. The history of science has a graveyard full of confident 3 sigma detections that evaporated under further scrutiny. Physicists learned this the hard way, which is why the field settled on 5 sigma as the gold standard for a confirmed discovery. 4.2 sigma sits between those 2 thresholds, past the zone of interesting anomaly, and deep into the territory of this needs a serious explanation. Getting from 3 to 4.2 sigma required something simple in concept and brutal in execution. More data, processed better, checked harder. The Cambridge team didn't run K2-18b's spectrum through an algorithm once and publish. Webb observed the planet across multiple transit events, each one lasting roughly 2.5 hours as the planet crossed the face of its host star. Every transit adds signal. Every additional observation reduces the statistical noise that could be masking or mimicking a molecular detection. Between the initial 2023 publication and the 2025 reanalysis, the team accumulated a larger baseline of transit data, applied more sophisticated atmospheric retrieval models, and ran the results through independent verification pipelines to confirm the signal wasn't an artifact of any single processing method. Two separate analytical teams worked from the same raw data without sharing intermediate results. A blind analysis structure designed specifically to prevent confirmation bias from contaminating the conclusion. Both arrived at the same fingerprint in the spectrum, 4.2 sigma, 99.7%. That path methodical, slow, deliberately skeptical is exactly what the magnitude of the claim demands. Now, consider what that signal implies at scale. Earth's oceans produce approximately 300 million metric tons of dimethyl sulfide every single year. 300 million tons released continuously by phytoplankton and microbial communities distributed across the entirety of our ocean surface. Every organism metabolizing, every colony exhaling this molecule upward into the atmosphere. That is the output of an entire planetary biosphere running at full capacity across every ocean on Earth simultaneously. And from interstellar distances, Earth's DMS signal is essentially undetectable. The concentration is real, but diffuse, spread thin across a planet that from 120 light-years away appears as a point of light smaller than a pixel. For K2-18b's DMS signal to register on Webb's instruments at that distance to generate a 4.2 sigma detection across 120 light-years of space, the atmospheric concentration has to be substantially higher than what Earth's oceans produce in a year. The modeling suggests the levels required to generate the observed spectral signature could be multiples of Earth's atmospheric DMS concentration, not a trace reading from an isolated microbial colony somewhere on the surface, something operating at a scale that would dwarf our entire marine biosphere. A planetary biosystem so extensive it has saturated the atmosphere of a world 8.6 times Earth's mass with the chemical exhaust of living processes. You're thinking maybe it's just a chemical reaction, some unusual photochemistry, some volcanic quirk specific to this type of planet, something outside our current catalog that produces DMS without biology. The scientists thought of that before you did. That is, in fact, exactly where they started. Every known abiotic pathway capable of generating sulfur-containing organic molecules was modeled against the specific conditions Webb has characterized in K2-18b's atmosphere. Photochemical reactions driven by the host star's ultraviolet radiation simulated and ruled out. The UV flux from a red dwarf like K2-18 follows a different spectral profile than our Sun, and under those precise conditions, the photochemical routes that might produce sulfur compounds simply don't generate dimethyl sulfide. The reaction pathways don't go there. Volcanic outgassing was evaluated next. Geological activity releases a range of sulfur compounds: sulfur dioxide, hydrogen sulfide, carbonyl sulfide, but not dimethyl sulfide, not in a hydrogen-dominated atmosphere, not at concentrations remotely close to what the spectrum shows. The thermodynamics of the relevant reactions under hydrogen-rich conditions work against DMS formation at every step. Meteoritic delivery was considered as well. Carbonaceous meteorites carry organic compounds including sulfur-bearing molecules, and large impacts can introduce chemistry that wouldn't otherwise develop on a planet's surface. but the quantities delivered through impact events are orders of magnitude too small to sustain a persistent atmospheric signature at detectable levels, and impact-delivered compounds don't replenish. They arrive in discrete events, get processed and broken down by atmospheric chemistry over time, and disappear. A sustained signal at 4.2 sigma implies a sustained source, something continuously producing and releasing DMS into the atmosphere on a timescale long enough to maintain equilibrium concentration. No geological process does that. No photochemical pathway does that. Biology does that. What makes the DMS detection genuinely decisive, though, is that it does not stand alone. Webb's spectrum of K2-18b simultaneously revealed elevated concentrations of methane and carbon dioxide, present at ratios that atmospheric equilibrium chemistry cannot account for through abiotic processes. This changes the nature of the evidence fundamentally. A single anomalous molecule, DMS, could, in principle, turn out to have some exotic non-biological source unique to Hycean worlds that science hasn't characterized yet. That possibility, however small, remains technically open while the sample size of studied Hycean worlds is 1. But DMS plus anomalous methane plus anomalous carbon dioxide, all simultaneously present, all at ratios inconsistent with what chemistry predicts for a lifeless planet that is a dual biosignature. 3 independent atmospheric signals, each one difficult to explain without biology, each one failing separately to yield to the same non-biological alternatives. The probability space for a natural, abiotic explanation that accounts for all 3 simultaneously collapses to something far smaller than any individual signal alone could achieve. Think of it as a witness problem. 1 witness placing someone at the scene is significant. 3 independent witnesses who never coordinated, each describing the same thing from different angles, that is, a different category of evidence entirely. K2-18b's atmosphere is giving science 3 witnesses. They are not contradicting each other. They are not pointing in different directions. They are converging on the same conclusion from 3 independent lines of chemical evidence. The signal is real. The source survives every non-biological explanation thrown at it. And the scale implied by what Webb measured suggests not a flicker of possible life in some sheltered corner of the planet, but something that has filled an entire world's atmosphere with the chemistry of living processes. But to understand why life could exist here at all, we need to look at the planet itself. Picture Earth from orbit. A blue marble, 71% of its surface water, a thin shell of nitrogen and oxygen wrapped around it, tilted slightly on its axis, circling a yellow star at just the right distance. Humans look at that image and call it perfect, life's ideal address. For decades, that image became the template, the blueprint, the only model planetary scientists had for what a habitable world was supposed to look like. So when the search for life beyond Earth began in earnest, the criteria built themselves naturally around it. Liquid water on the surface essential, moderate temperatures, somewhere between freezing and boiling required, rocky composition, similar mass to Earth preferred, a yellow or orange star, stable, not too energetic strongly recommended. The checklist was logical, internally consistent, and built entirely on a sample size of 1. K2-18b violates every item on that list. Its mass is 8.6 times Earth's. Its radius is 2.6 times larger. By the old framework, it would have been dismissed early too massive. Gravitational field too strong. Atmosphere too thick for any meaningful surface chemistry. Planetary scientists would have noted it, filed it, and moved on. Instead, it has a classification that didn't exist in the working vocabulary of astronomy. Until recently, a Hycean world. The name compresses 2 words to hydrogen and ocean into a single category for a type of planet that models now suggest may be far more common in the galaxy than rocky Earth analogs, but which had no framework for serious consideration as a life candidate until the last several years. The defining features are exactly what the name implies: a deep global ocean covering the entire surface with no continents, no exposed rock, no land of any kind, and above it, a thick hydrogen-dominated atmosphere bearing down with substantial pressure. K2-18b's ocean, if it exists as models predict, is not like any ocean you can stand beside. It has no shoreline, no beaches, no continental shelves, no bottom reachable by any submersible humans have ever built. It could extend downward for hundreds of kilometers before pressure and temperature conditions shift water into exotic high-pressure phases that no marine biology textbook has ever needed to address. An ocean hundreds of kilometers deep. Can you picture what the bottom of that looks like? Neither can the scientists, not with any confidence. And that honest uncertainty is itself one of the most exciting things about this planet. The hydrogen atmosphere sitting above that ocean changes the thermal physics of K2-18b in a way that makes everything else possible. Hydrogen is an exceptional insulator, more efficient at trapping heat than carbon dioxide, more efficient than the nitrogen-oxygen mix blanketing Earth. A thick hydrogen envelope around a planet acts like a blanket of a density and completeness that Earth's atmosphere simply cannot match, pressing in from all sides, holding thermal energy close to the surface regardless of how much or how little starlight arrives from outside. K2-18b orbits its red dwarf host at a distance that, around a sun-like star, would leave its surface frozen solid. The stellar energy arriving at that orbital distance is substantially weaker than what Earth receives. Under standard planetary physics, with a nitrogen or carbon dioxide atmosphere, the surface temperature would fall well below water's freezing point. The hydrogen atmosphere overrides that calculation. That insulating envelope captures enough of the limited incoming stellar energy to maintain surface temperatures around 49 degrees Celsius, stable, persistent, consistent across the planet's long orbital history, and critically above the freezing point of water, by a margin sufficient to sustain a global liquid ocean across timescales measured in billions of years. 49 degrees Celsius sounds hostile. If the life you're imagining resembles you, it probably is. But life does not have to resemble you. It doesn't even have to resemble anything in a standard biology textbook. On Earth, organisms called thermophils, heat-adapted extremophiles, live and thrive at temperatures between 60 and 80 degrees Celsius in hot springs, hydrothermal vents on the ocean floor, and volcanic environments. Some archaeal species have been documented surviving above 90 degrees Celsius. These are not desperate organisms clinging to the margins of possibility. They are metabolically active, reproducing evolutionarily successful life forms that have occupied their thermal niches for hundreds of millions of years. For them, Earth's temperate surface zones would be uncomfortably cold. In an ocean hundreds of kilometers deep, temperature is not a single fixed value. The surface layer at 49 degrees Celsius is the warmest region, exposed to the most stellar energy. Deeper layers, insulated from above and governed by the planet's internal heat dynamics, would be progressively cooler as you descend. A planetary ocean of that vertical extent contains an enormous range of thermal environments, stacked one beneath the other, each potentially hospitable to different biochemistries, different metabolic strategies, different organisms operating under conditions Earth biology has no reference point for. The ocean of K2-18b is not an obstacle to life. It may be the largest and most thermally diverse potential habitat ever identified in the history of exoplanet research. But an ocean alone, even a planetary one, is just a container. Without something driving chemistry, powering metabolism, Sustaining the energetic cycles that life requires to persist across geological time, it remains an empty vessel. What provides the stable, continuous energy source that could keep K218b's potential biosphere running across billions of years is genuinely where this story gets truly insane. The pressure at the base of K218b's hydrogen atmosphere is not a detail. It is the entire reason the ocean beneath it can exist at all. To understand this, start with something in your kitchen. A pressure cooker. Seal water inside one. Apply heat, and the water inside doesn't boil at 100 degrees Celsius, the temperature at which it would boil in an open pot at sea level. Because pressure increases inside the sealed vessel, the boiling point rises. The water stays liquid at temperatures that would turn it to steam under normal conditions. The physics is straightforward. Pressure suppresses phase transitions. The higher the pressure, the more thermal energy water can absorb before it changes state. Now scale that principle to a planetary atmosphere 8.6 times the mass of Earth. Pressing down on an ocean from above with a weight that dwarfs anything in our atmospheric experience. The base of K218b's hydrogen envelope exerts pressure on the ocean surface far exceeding anything Earth's atmosphere generates at sea level. That pressure envelope does exactly what a pressure cooker does. It suppresses boiling, forces water to remain liquid even at surface temperatures that would otherwise drive evaporation and atmospheric loss. The ocean stays, the liquid layer is stable, and stability across geological timescales is the prerequisite for everything else. In 2023, Professor Niku Madhusudan's team at the University of Cambridge published modeling simulations of K218b's interior and ocean structure. The results were layered in a way that reads almost like a cross-section of an entirely alien world, because that is precisely what it is. The upper ocean layer, the region where stellar energy and atmospheric pressure interact directly, maintains liquid water in a stable state consistent with the temperatures Webb's observations imply. This is the zone where, if biology exists on K218b, it almost certainly concentrates close enough to the light source for photochemical energy to be available, warm enough for chemical reactions to proceed at meaningful rates. Protected from direct stellar radiation by the thick hydrogen atmosphere above. Go deeper, and the pressure climbs. Keep going, and you reach conditions that have no equivalent anywhere in Earth's natural environment. Pressure so extreme that water itself stops behaving like water. The molecular structure distorts. The oxygen atoms lock into a crystalline lattice, while the hydrogen protons become mobile, flowing through the fixed oxygen framework like a current through a conductor. This is superionic water, a state of matter that exists simultaneously as solid and liquid, conducting electricity, behaving in ways that the word water was never designed to describe. It has been produced briefly in laboratory conditions using high-powered lasers compressing water to extreme pressures. It has never been observed occurring naturally on Earth. K218b may have an ocean of it at depth, sitting beneath the liquid layer above like a hidden basement under a house. If superionic water can exist, who can say with any confidence that life cannot form inside it? The honest answer is nobody can. Biology as we understand it requires liquid water, a solvent, an energy gradient, and chemical complexity sufficient to support self-replication. Whether superionic water satisfies those requirements is a question that current science cannot answer, because the conditions required to study it in any sustained way are beyond what laboratory equipment can maintain. The boundary of the question is also the boundary of the instruments. And whenever that happens in science, the correct response is not to assume impossibility. It is to acknowledge that the space for possibility remains open. We spent the better part of a century searching for an Earth 2.0, a planet with continents and seasons, and a comfortable ocean you could sail across on a weekend. The universe apparently had something else in mind entirely. an Earth 8.6 times version, with a bottomless swimming pool instead of a backyard, wrapped in a hydrogen blanket, sitting around a star that burns so faintly, it barely registers as a star at all by the sun's standards. We set up very specific expectations. The universe ignored them completely and handed us something more interesting. The statistical implications of the Hycean world model reach beyond K2-18b as an individual case. For decades, the search for potentially habitable exoplanets focused predominantly on rocky worlds in the classical habitable zone, the orbital range where a planet around a sun-like star could maintain liquid surface water. That search yielded meaningful results, but the catalog of confirmed rocky Earth analogs in true habitable zones remains small. The conditions required to produce one are stringent. The right stellar type, the right orbital distance, the right planetary mass range, the right geological history. Hycean worlds require a different set of conditions, and those conditions appear to be far less rare. Statistical modeling of the known exoplanet population suggests that somewhere between 35 and 40% of super-Earth's planets, between roughly 2 and 10 times Earth's mass orbiting within their star's habitable zone, may be Hycean worlds. Not confirmed, not observed directly in each case, but consistent with what planetary formation models predict for planets in that mass and composition range. 35 to 40% of a very large number is an enormous number of potential habitable environments. Environments that the old search criteria would have passed over without a second look. K2-18b is not an outlier discovered despite being the wrong kind of planet. It may be a representative of the most common type of habitable world in the galaxy, one that we simply didn't have the framework to recognize until now. The implications of that reframing for the broader search for life are difficult to overstate. Every catalog of potentially habitable planets built on the old criteria is now incomplete in a way that has nothing to do with observational gaps. It was incomplete by design because the design was too narrow. The galaxy may be full of ocean worlds we dismissed as too big, too hydrogen-rich, too different from the only template we knew. K2-18b is the first one to talk back, but a planetary ocean is only the stage. The star lighting it is where the real story begins. Our sun will live for approximately 10 billion years. We are currently halfway through that lifespan. 4.6 billion years have already passed. Life on Earth required roughly 3.8 billion years to travel from the first self-replicating molecules to the species now pointing telescopes at distant stars. That timeline consumed nearly the entire first half of the sun's existence. It was close, not comfortably. Close, uncomfortably close, in the sense that if Earth had formed even 500 million years later, the question of whether complex life had time to emerge before the sun's increasing luminosity destabilizes the climate becomes genuinely uncertain. Time is evolution's most essential raw material. Without enough of it, complexity cannot accumulate. Mutations need generations to be tested. Adaptations need environmental pressure sustained across millions of years to select for meaningful change. The entire 4 billion year story of life on Earth, from anaerobic bacteria in ancient oceans to everything walking, swimming, and flying on the planet today, is fundamentally a story about what happens when chemistry has enough time to iterate. Take away sufficient time, and you don't get a slower version of that story. You get no story at all. K2-18's host star is a red dwarf, spectral class M. Its estimated lifespan between 3 trillion and 10 trillion years. Sit with those numbers for a moment. The universe is currently 13.8 billion years old. That is the entire age of everything, every galaxy, every star, every atom that has ever fused in a stellar core since the Big Bang. K2-18, the dim red star that K2-18b orbits, will still be burning when the universe is 1,000 times its current age. it will outlive every sun-like star that exists today. It will outlive the conditions required for new sun-like stars to form. In the cosmological long run, red dwarfs are not minor characters. They are the last lights that will remain on when the rest of the stellar population has gone dark. Now imagine you are not given 70 years to learn a skill, but 700,000 years. Not a human lifetime, not a civilization's lifespan. 700,000 years of uninterrupted practice, selection, refinement, iteration. How good would you be? The question becomes meaningless because good stops being a useful category after enough time. You would be something unrecognizable from your starting point. Red dwarfs burn their fuel at a rate so conservative it borders on the surreal. A star like our sun fuses hydrogen in its core at a prodigious rate, burning bright, burning hot, burning through its fuel supply on a 10 billion year schedule that feels long by human standards, but is a brief flash by stellar ones. A red dwarf operates nothing like this. Its core temperature is lower. Its fusion rate, a small fraction of a sun-like star's. Its energy output dim enough that you could stare at K2-18 directly and see only a faint reddish point rather than the blinding disk our sun presents. That dimness is the point. It is the signature of extraordinary efficiency, a stellar engine running at such a measured pace that its fuel supply extends not into the billions, but into the trillions of years. Think of it as the difference between a bonfire and a candle sealed inside a lantern. The bonfire burns brighter and hotter, but it exhausts itself in an evening. The candle, protected and measured, burns through the night and into the following day, and keeps burning long after anyone expected it to still be lit. K2-18 is that candle. It has been burning for billions of years already. It has trillions more ahead of it. And for every year it burns, K2-18be receives a steady, consistent, predictable supply of energy, no dramatic changes in luminosity, no sudden shifts in the radiation environment, no stellar aging process accelerating the warming of its planetary system toward an uninhabitable threshold. If life exists on K2-18b today, it has almost certainly been evolving for longer than Earth has existed. Earth formed 4.5 billion years ago. K2-18b's age has not been precisely determined, but red dwarf systems commonly form early in galactic history, and the planet may be older than our solar system by a significant margin. Life on K2-18b, if it began early in the planet's history, has potentially had more time to evolve than the entire age of Earth, running its biological iterations not across 4 billion years, but across a time frame that could exceed that several times over. What does biology look like after 10 billion years of uninterrupted evolution in a stable ocean? We have no comparison. Earth's 4 billion year experiment produced everything from blue-green algae to the human brain, a range of complexity that staggers the imagination when you trace it in full. Extending that process by another factor of 2 or 3 in a thermally diverse ocean the size of a planet, under conditions we have never studied, produces outcomes that our current conceptual vocabulary is not equipped to describe, not because the biology would necessarily be more intelligent or more complex in ways we recognize, but because the directions evolution can take across that kind of time scale, under that kind of environmental pressure, with that much opportunity for novelty to accumulate, lie genuinely outside the boundary of what we can model or predict. The universe has been running an evolutionary experiment on K2-18b for longer than Earth has existed. We are only now noticing that the experiment appears to be active. But red dwarfs carry a dark side, and the answer to that paradox is what makes this genuinely shocking. Red dwarfs are not born calm. That is the paradox buried at the center of everything that makes K2-18be seem like a perfect candidate, and it nearly disqualifies the entire case before it begins. In their youth, Red dwarfs are violent, genuinely, catastrophically violent, during the first few 100 million years of their existence, before they settle into the long, measured burn that defines their mature phase. Red dwarfs release enormous quantities of ultraviolet radiation and X-rays stellar flares that dwarf anything our comparatively well-behaved sun produces. These eruptions are not occasional. They are frequent, intense, and sustained across timescales long enough to do serious damage to any planetary atmosphere sitting within range. The technical term for this phase is the pre-main sequence period. The more accurate description is a tantrum, a prolonged, energetic outburst from a young star that hasn't yet learned restraint. For planets orbiting red dwarfs, this early period is the existential test. The radiation strips hydrogen from upper atmospheres. Intense X-ray flux ionizes atmospheric particles and drives them into space through a process called atmospheric escape. Planets caught in this phase without adequate protection can lose their atmospheres entirely, leaving behind bare, irradiated rocks incapable of supporting any chemistry complex enough to be called biology. It has happened in our own solar system. Mars likely suffered a version of this fate, its thin atmosphere gradually eroded by solar wind over billions of years. So when you learn that K2-18b orbits a red dwarf, a class of star notorious for this early radiation violence, the natural response is to question everything that came before. You're thinking the radiation would have destroyed everything. The atmosphere, the ocean, the chemistry. Nothing survives that kind of bombardment. Wait, K2-18b has a shield you haven't considered yet. The same hydrogen atmosphere that insulates the planet's surface, that maintains liquid ocean temperatures against the cold of deep space, that traps the limited stellar energy arriving at K2-18b's orbital distance. That same atmosphere functions simultaneously as a radiation barrier of extraordinary effectiveness. Hydrogen absorbs and scatters ultraviolet radiation. A thick hydrogen envelope surrounding a planet intercepts incoming UV and X-ray flux at altitude, high above the ocean surface, dissipating the energy before it can penetrate to the liquid layer below. Earth relies on a relatively thin ozone layer, a band of triatomic oxygen molecules, roughly 15 to 35 kilometers above the surface to absorb the sun's ultraviolet output. That thin shield is sufficient for our purposes because our sun's UV output is relatively modest by stellar standards. K2-18b's hydrogen atmosphere is not a thin chemical layer. It is a deep, dense, planet-enveloping mass of gas that extends far higher and presents far more absorbing material to incoming radiation than Earth's ozone layer ever could. The comparison undersells the difference. Earth's ozone layer is a coat. K2-18b's hydrogen atmosphere is a fortified wall. Calculations published by a research group at MIT in 2024 quantified this effect directly. Their modeling showed that a hydrogen atmosphere of the thickness Webb has characterized around K2-18be reduces ultraviolet flux at the ocean surface to levels safe for aquatic life within just a few meters of depth. Not kilometers down, a few meters. Any organism living in the upper ocean layer, even relatively close to the surface, would be shielded from the radiation doses that the young K2-18 star historically produced during its flaring phase. The ocean itself provides additional protection water, absorbs UV efficiently, and even shallow depth offers meaningful attenuation of whatever residual radiation the hydrogen atmosphere doesn't intercept first. The planet arrived at this solution not through any deliberate design, but through physics. The same mass and composition that make K2-18b so different from Earth, the thick hydrogen envelope, the deep global ocean, turn out to be precisely the features that allow it to survive the one environmental challenge that most threatens red dwarf planets. It is as though the hazard and the solution were engineered to cancel each other out. The thermal blanket is also, it turns out, the cosmic helmet. K218b is more thoroughly protected than any planet in our solar system, designed by circumstance for exactly the conditions it faces. Crucially, that violent early phase is over. K218 has aged past its pre-main sequence period. The stellar tantrums have subsided. The frequency and intensity of flare events have declined dramatically as the star settled into its mature main sequence phase, the long, stable burning period that will define its character for the next several trillion years. Current measurements of K218's activity level show a star that is, by red dwarf standards, remarkably quiet. The radiation environment at K218b's orbital distance today is not the bombardment that characterized the system's early history. It is steady, low intensity, consistent, the kind of energy input that biology can work with rather than be destroyed by. The window that mattered the dangerous early phase closed. The planet survived it, protected by its own atmospheric mass. What remains is a stellar environment of extraordinary stability, a dim, cool, long-lived star delivering a predictable, gentle energy supply to an ocean world that has already proven it can handle the worst the star had to offer. The danger past. The stability that follows will last longer than the current age of the universe. A perfect planet orbiting a perfect star. But this forces us to ask the question all over again, what does perfect actually mean? Starting in the 1990s, when the first confirmed exoplanet detections began to accumulate, the search for potentially habitable worlds operated on a clear and seemingly logical framework. The target was specific: a rocky planet, roughly Earth-sized, orbiting a G-type yellow star like our Sun, positioned within the habitable zone, close enough to its star for liquid water to exist on the surface, far enough to avoid being scorched. The Goldilocks zone. Not too hot, not too cold, just right. The framework had the appeal of simplicity. It made the search tractable. Astronomers knew what they were looking for and could filter candidate planets accordingly. Over 3 decades, it drove the design of instruments, the prioritization of telescope time, and the structure of the catalogs that organized the growing list of confirmed exoplanets. The framework was built entirely on a single data point: one planet, one biosphere, one case study generalized into a universal standard for what habitable means. That is not a criticism unique to astronomy. It is the fundamental epistemological trap of any field, working from a sample size of 1. You observe the only example you have, extract its properties, and treat those properties as requirements. It is logical, given the constraint. It is also almost certainly wrong, and the wrongness only becomes visible when a second data point arrives that refuses to fit the template. K218b is that second data point, and it fits nothing. Not rocky, not Earth-sized, not orbiting a yellow star. Mass 8.6 times Earth's radius, 2.6 times larger. Circling a dim red dwarf on a 33-day orbital period. By every criterion, the search framework established over 30 years. K218b should have been a low-priority background entry in a catalog noted, filed, and left for later consideration while better candidates were pursued. Instead, it is the strongest candidate for an inhabited world beyond Earth that science has ever identified. 99.7% confidence on a biosignature detection, a dual chemical signature that resists every non-biological explanation, an atmospheric composition in active disequilibrium, an ocean that may cover an entire planetary surface, a stellar environment now stable enough to sustain biological processes across billions of years. The planet that breaks every rule is the one that may have given us the answer we spent 3 decades looking for in the wrong places. If every criterion we established was wrong, how many living worlds did we pass over in 30 years of searching? That question does not have a comfortable answer. It doesn't have any precise answer yet. but the logic it implies is damaging to the confidence with which the search has historically been conducted. Every catalog compiled under the old framework is now suspect, not because the observations were wrong, but because the interpretive layer applied to them was too narrow. Planets were ranked, deprioritized, or excluded based on properties that K218b demonstrates are not actually disqualifying. The filter itself was the problem. The analogy that captures this most cleanly is the Arctic. Imagine you need to find living animals in the Arctic, but your search method consists entirely of looking for elephants. You design your instruments to detect the size, shape, and thermal signature of an elephant. You train your observers to recognize elephant behavior. You compile a catalog of Arctic regions where elephant habitat might theoretically exist. And you find nothing, because nothing in the Arctic is an elephant. Polar bears are there, walruses, Arctic foxes, narwhals moving under the ice, seabirds in numbers that exceed anything the African savanna supports. The Arctic is full of life. Your search found none of it, because you defined life as elephant-shaped before you started looking. This is what 30 years of exoplanet habitability searches did, at least in part. The search was designed around a specific life signature profile: rocky, Earth mass, sun-like star, and everything that didn't match that profile received diminished attention. Hycean worlds were in the catalog the whole time. K218b was discovered in 2015 by the Kepler Space Telescope. It sat in the database for 8 years before Webb looked at its atmosphere and found what was waiting there. 8 years, 120 light-years away. The signal was always there. The instrument to read it didn't exist yet, and the conceptual framework to prioritize it wasn't quite in place either. What the Hycean world category opens is not a minor expansion of the existing search list. It is a structural revision of the question itself. When between 35 and 40% of super-Earth's inhabitable zones may be Hycean worlds, and when Hycean worlds appear to be more thermally stable, more radiation-resistant, and longer-lived as habitable environments than rocky Earth analogs, the implication is not that we were close and needed a small correction. The implication is that the most common type of habitable world in the galaxy is precisely the type we were systematically undervaluing. The galaxy may not be sparse with habitable worlds. It may be full of them, in a form we weren't looking for. K218b didn't just change the answer, it changed what we understand the question to be. But redefining habitable worlds is only the surface of what this discovery ruptures beneath it. Lies a far deeper revolution in how we understand what life itself is. The number sitting at the center of this story is 99.7%. That number gets the headlines. It deserves them. But there is a second number, quieter and in some ways more consequential, that the coverage tends to pass over 5,000. As of the 2024 NASA Exoplanet Archive update, astronomers have confirmed more than 5,000 exoplanets orbiting stars beyond our Sun. 5,000 worlds, logged across decades of observation, cataloged by mass and radius, and orbital period, and host star type, sorted into priority tiers that were supposed to tell the scientific community which ones deserved the most attention. For most of that catalog's existence, the sorting logic was built on the old framework: rocky, Earth-sized, sun-like star, classical, habitable zone. Planets outside those parameters moved down the list, not because anyone decided they were impossible candidates, because the framework didn't have a category for them that flagged them as worth prioritizing. Apply the revised Hycean world criteria to that 5,000, and between 15 and 20% of those confirmed exoplanets may be candidates that deserve serious atmospheric reanalysis. Work through the arithmetic plainly. 15% of 5,000 is 750 worlds. 20% is 1,000. These are not hypothetical planets waiting to be discovered, they are already in the database. already observed, already cataloged. They were filed under classifications that didn't raise a flag, not because the data was wrong, but because the interpretive layer sitting above the data was too narrow to recognize what it was looking at. The previous 30 years didn't fail to find these planets. They found them, logged them, and looked past them. That is the first implication of K218. Not the biosignature reading itself, but what the biosignature reading reveals about the scale of what the old framework was missing. The search wasn't underfunded or technically inadequate. It was filtering for the wrong shape. Every catalog compiled under the assumption that habitable means Earth-like is now a document with hundreds of entries that need to be reopened and looked at again with different eyes. You might be thinking we still don't actually know K218b has life. 4.2 sigma is not 5 sigma. The detection is compelling, but not confirmed by the gold standard of physics, and building sweeping conclusions about the galaxy's habitable planet population on a single unconfirmed biosignature candidate seems premature. The honest scientific response is to wait for the 5 sigma threshold before claiming the question is answered. That objection is correct on the narrow point and misses the larger one entirely. Whether or not life is ultimately confirmed on K218 on TEE, the planet's existence as a serious candidate has already changed something irreversible: the baseline probability. Before K218b entered the picture as a live candidate, the working assumption embedded in habitability research, never formally stated, but structurally present in how resources were allocated and catalogs were organized, was that non-rocky, hydrogen-dominated, high-mass planets were low-probability environments for biology. Not impossible, low priority. The prior was never explicitly set to 0. It was treated as negligible by the structure of the search itself. K218b has moved that prior. A planet carrying a 4.2 sigma biosignature detection, resistant to every non-biological alternative proposed against it, is not a negligible candidate. It is the strongest candidate in the history of the search. And if life can emerge in conditions that different from Earth, a hydrogen ocean world 8.6 times Earth's mass, no surface land, no rocky substrate, orbiting a dim red dwarf, then the term F sub L in the Drake equation needs to be recalculated against a much larger eligible planet population than the equation was designed around. The Drake equation's F sub L represents the fraction of planets with suitable conditions where life actually emerges. For decades, suitable conditions was implicitly defined against Earth. If Hycean worlds qualify, and K218b is providing the strongest available evidence that they do, then F sub L applies to a candidate pool that is not dozens or hundreds of planets larger than previously estimated. It is potentially hundreds of thousands larger, distributed across the galaxy in the form of super-Earths that previous searches cataloged and deprioritized. The number of worlds where the origin of life could occur doesn't increase gradually when you expand the definition of habitable. It jumps, because the category of eligible planets was being artificially constrained by a definition built on one example. There is a useful way to illustrate what happened here. Imagine someone who has spent their entire life in Texas, never left the state, never had reason to, and decides, on the basis of that experience, that every worthwhile city must have open ranch land, cattle operations, and a reliable supply of cowboy hats. They build a global city ranking system around those criteria. Dallas scores well, Fort Worth passes, San Francisco gets flagged as a weak candidate, no cattle, dubious hat situation. Tokyo is essentially unranked. Paris receives a question mark. The guide is internally consistent. It reflects everything the author genuinely knows. It is also completely useless as a framework for understanding cities, because the author took the specific features of their single reference point and mistook them for universal requirements. Strip away the flattering framing, And that is a reasonably accurate description of 3 decades of exoplanet habitability research. Not irrational. It was the only framework available, built from the only inhabited world ever studied. But a framework derived from one example cannot survive contact with a second example that looks nothing like the first. K218b is that second example, and it has arrived carrying the strongest biosignature reading ever recorded. One detail that rarely surfaces in the public coverage of the Webb telescope's K218b results, but which belongs in this story. Webb was not a general-purpose observatory that happened to point at this planet by luck. The telescope's infrared sensitivity range, its 6.5-meter gold-coated primary mirror, its NIR spec and MIRI spectrographic instruments. These were specified with the explicit scientific goal of analyzing the atmospheric composition of planets around dim stellar hosts, including red dwarfs, including hydrogen-dominated super-Earths. The science case for Hycean worlds as high-value targets existed in the literature before Webb launched. The astronomers who defined the telescope's technical requirements understood that hydrogen-rich atmospheres around massive super-Earths represented a class of planets worth being able to read. They built the instrument accordingly, a decade before it reached space. Webb finding the DMS signal on K218b was not serendipity. It was the designed outcome of a 25-year, $10 billion instrument development program aimed, in part, precisely at this type of planet. The detection was planned for, the capability was built deliberately, and because that capability exists and will continue operating for another decade or more, K218b is not the end of this story. It is the opening entry in what may become a catalog of Hycean world atmospheric readings, each one contributing additional data points to the question that K218b has put so forcefully on the table. The planet and the star have been covered. The search framework has been revised. The biosignature candidate stands at 4.2 sigma and climbing. But the thing that truly overturns everything is not the planet and not the star. It is what is happening inside the atmosphere of K218b right now. Take a breath. Right now, wherever you are, take one slow breath in. You just pulled oxygen out of the room around you. In a few seconds, you will push carbon dioxide back into it. The chemical composition of the air in your immediate vicinity has shifted by a small but physically real amount, because you are alive and the act of being alive is chemically disruptive. You cannot stop doing this. Your body runs on the continuous transformation of one set of molecules into another, consuming ordered chemical energy and releasing waste products that are measurably different from what went in. Every breath is a small chemical disturbance, repeated roughly 16 times per minute, sustained without interruption for as long as you live. Multiply that across 8 billion humans. Add every insect on every continent, every fish in every ocean, every bacterium in every gram of soil, every phytoplankton cell in every surface layer of every sea, every tree running photosynthesis and exhaling oxygen, every termite digesting wood and releasing methane, every microbe metabolizing organic compounds and venting sulfur byproducts upward into the atmosphere. All of it happening simultaneously, continuously, at every point on the planet's surface and through every meter of its ocean column. The cumulative effect is that Earth's atmosphere never reaches chemical equilibrium. It cannot. The biological disruption is too large, too distributed, too unceasing. The atmosphere of a living planet is, in a precise thermodynamic sense, permanently out of balance, held there by the collective metabolic activity of everything alive, every moment of every day. A dead planet runs on entirely different chemistry. Without biology continuously interrupting the system, molecular species react with each other, concentrations stabilize, reactive compounds get consumed and stable ones accumulate, and the atmosphere settles into the state that thermodynamics and photochemistry predict from first principles, given enough time. A lifeless planet's atmosphere reaches equilibrium, not perfect stasis, because stellar radiation and geological outgassing continue to add inputs, but a predictable steady state that atmospheric models can fully account for without invoking biology. The chemistry is, in a word, boring, consistent, explainable, a closed system running toward its lowest energy configuration, undisturbed by anything that breathes. Webb looked at K2-18b's atmosphere. What it found cannot be described as boring. Methane, CH4, is present at concentrations substantially elevated above what abiotic atmospheric chemistry predicts for a hydrogen-dominated world at K2-18b's pressure and temperature. Carbon dioxide is also elevated, present at ratios inconsistent with equilibrium predictions for a planet of this composition. These two molecules coexist in K2-18b's atmosphere at levels that, without continuous replenishment, would decay through chemical reactions on timescales far shorter than the planet's age. Their sustained presence at observed concentrations implies a source actively maintaining them, something continuously producing or preventing the depletion of both across the entire atmospheric column over geological time. Then there is ammonia. Nitrogen is present in K2-18a's atmosphere. Hydrogen is abundant. It is the dominant atmospheric component. Under the pressure and temperature conditions Webb has characterized, the thermodynamically predicted outcome of nitrogen and hydrogen coexisting in a hydrogen-rich environment is ammonia formation, NH3. The reaction is favored. The ingredients are present. The product should be there. It is almost entirely absent. If there is no life on K2-18b, what is continuously breaking the chemical equilibrium of an entire planet? That question carries a different weight than asking about DMS alone. DMS is a biosignature because of its exclusive biological origin. The disequilibrium question is a biosignature because of what it reveals about the system as a whole. A planet whose atmosphere persistently refuses to behave the way dead planet chemistry predicts is a planet where something is continuously interfering with chemistry at scale, not locally, not intermittently, globally, persistently, across the full atmospheric column that Webb's transmission spectroscopy reads when starlight filters through the planet's rim. Think of a sealed room. No windows, no ventilation, nobody inside. Lock it for a month. Come back. The air composition is predictable oxygen slightly depleted by slow surface reactions, carbon dioxide at an equilibrium level, humidity stable against the walls. The chemistry is settled, nothing is disrupting it. Now put a person in that room. Add a small garden, a cooking fire. Come back in a month. The air is entirely different oxygen being consumed and regenerated. Carbon dioxide cycling with the plants, methane from the soil microbes, water vapor fluctuating. The room's atmosphere is not in equilibrium and cannot be, because everything living inside it is continuously preventing equilibrium from occurring. The room is chemically alive because something in it is alive. K2-18b is a room 8.6 times the mass of Earth. Its atmosphere is the disrupted one, not the settled, predictable chemistry of an empty space, but the complex, reactive, persistently anomalous chemistry of a system where something is continuously operating against equilibrium. The scale of the disruption, read across the entire atmospheric column by Webb's instruments from 120 light-years away, does not suggest a localized anomaly in one sheltered region of the ocean. It suggests a source distributed widely enough to leave its fingerprint on the atmospheric composition of an entire world. The ammonia deficit is particularly telling, and it deserves to be treated separately from the methane and carbon dioxide elevations. The absence of ammonia is not simply a missing data point. It is a specific, directional absence. Something that thermodynamics says should be present is not present, and for which the non-biological explanations fall short. Photolytic destruction of ammonia by stellar ultraviolet radiation is a real process. K2-18's radiation environment has been characterized well enough to model the rate at which UV flux would break down atmospheric ammonia. The modeled photolytic destruction rate does not account for the scale of the observed deficit. The numbers do not close. There is a gap between what photochemistry predicts should remain and what Webb actually measured, and that gap requires an additional ammonia. Sink something removing ammonia from the atmospheric budget faster and more thoroughly than radiation alone can explain. On Earth, that additional sink is biological. Microbial nitrification converts ammonia to nitrate. Biological assimilation incorporates it into amino acids and proteins. The collective metabolic activity of Earth's microbial biosphere is so effective at consuming atmospheric ammonia that concentrations remain at trace levels despite continuous geological and agricultural production. The mechanism is well understood. The scale of the biological ammonia sink on Earth is quantified, and the character of the ammonia deficit observed on K2-18TeB a shortfall below thermodynamic predictions that photochemistry alone cannot bridge is, in its structure, consistent with exactly that kind of biological consumption operating at planetary scale. 3 signals: methane anomalously elevated, carbon dioxide anomalously elevated, ammonia anomalously absent, each one individually inconsistent with abiotic equilibrium predictions, all 3 present simultaneously in the same atmosphere, none of them yielding to the same non-biological explanation. The probability that all 3 arise together through purely abiotic processes, calculated by Shortall and colleagues at Cambridge in 2024, is below 0.3%. That is the number on the other side of 99.7. It is the residual left after running every available non-biological atmospheric model against the full set of observed anomalies and finding that none of them close the gap. One coincidence is conceivable. 2 simultaneous coincidences pointing in the same direction starts to require explanation. 3 simultaneous coincidences, each independently anomalous, all consistent with the same biological interpretation, combined yielding a probability below 0.3%. The universe does not generate patterns like that by accident. K2-18b is essentially breathing at global scale. Its atmosphere is carrying the chemical exhaust of living processes distributed across an entire planetary ocean, rising through hundreds of kilometers of hydrogen and hydrogen into a spectroscopic signal readable from interstellar distance. We caught it doing exactly this, not by landing on it, not by sending a probe, not by any method that required crossing the 120 light years separating us from it. We caught it by reading the gaps in starlight. But to understand why that method of catching it is itself extraordinary, we need to understand the instrument that made it possible. Carl Sagan didn't wait for Webb. In 1993, 30 years before the Cambridge team published their K2-18b results, Sagan and a group of colleagues turned the Galileo spacecraft's instruments toward Earth during a gravitational assist flyby and asked a deliberately uncomfortable question: if we didn't already know life existed here, would we be able to tell from the data alone? The answer was yes, and the reason wasn't any single molecule. Sagan's team found that Earth's atmosphere contains methane and oxygen simultaneously, 2 molecules that react aggressively with each other and destroy one another on timescales of a few million years. Their coexistence in measurable sustained concentrations is chemically impossible without continuous biological replenishment. Methane gets oxidized. Oxygen gets consumed in the process without something continuously restoring both. They disappear from the atmospheric budget on a geological blink. No abiotic process has ever been identified that produces and maintains both at the observed Earth concentrations simultaneously. The atmosphere holds two incompatible molecules in stable disequilibrium, and the only explanation that survives full scrutiny is that something alive is continuously reintroducing both of them photosynthesis on one side, methanogenic microbes on the other, running in parallel, neither one winning. The tension between them sustained indefinitely by biological activity. That paper, published in Nature in 1993, established the theoretical backbone of what planetary scientists now call the dual biosignature framework. The most reliable marker of life is not one anomalous molecule, but a combination of molecules whose simultaneous presence cannot be reconciled with lifeless atmospheric chemistry. The logic has held without serious challenge for 3 decades. No laboratory experiment, no planetary atmosphere model, no observation of any other body in the solar system has produced a genuine abiotic counterexample, a non-biological system that generates and sustains a dual biosignature at detectable concentrations. The combination is, as far as accumulated scientific evidence can determine, a marker that only biology produces. K218b carries a version of that same argument, translated into its own atmospheric chemistry. The molecules are different because the planet is different. K218b's atmosphere is hydrogen-dominated and oxygen-free, so the methane-oxygen pairing that flags Earth as inhabited doesn't apply directly. What the planet offers instead is its own incompatible trio: methane elevated beyond equilibrium predictions, carbon dioxide elevated beyond equilibrium predictions, and ammonia absent where equilibrium chemistry says it must be present. 3 signals, each one anomalous on its own terms, none of them yielding to the same non-biological explanation, and all 3 simultaneously present in the same atmospheric column, read in the same data set, pointing in the same direction. The structure of the argument is identical to Sagan's 1993 paper. The chemistry is different because the planet is. The logic is the same molecules whose observed concentrations cannot be reconciled with abiotic atmospheric models are present at those concentrations anyway. And the explanation that survives after eliminating alternatives is biological activity. One coincidence. One atmospheric anomaly that defies equilibrium predictions is scientifically significant, but manageable. Models have gaps. Instruments have calibration uncertainties. A single anomaly generates a hypothesis worth investigating and a program of follow-up observations. It does not, on its own, close the case. 2 simultaneous coincidences pointing in the same direction is a different problem. The probability that 2 independent chemical inconsistencies share the same non-biological explanation, neither one connected to the other, both arising together by coincidence in the same atmosphere, is substantially smaller than either one alone. 2 anomalies don't add their probabilities. They multiply the difficulty of the alternative explanation. 3 simultaneous coincidences, each independently resistant to abiotic models, all present together, all consistent with the same biological interpretation. The universe does not play dice that way. The modeling that puts a number on this comes from Shortall and colleagues at Cambridge, published in 2024. Running every available non-biological atmospheric model against the full set of 3 observed anomalies, simultaneously methane elevation, carbon dioxide elevation, ammonia deficit. They calculated the residual probability, the likelihood that all 3 arise together through purely abiotic processes under the pressure, temperature, and compositional conditions Webb has characterized for K218b's atmosphere. The figure they arrived at is below 0.3%. That number is not an expression of wishful thinking. It is the remainder left after the alternatives have been exhausted. You do not reach 0.3%. by hoping life is there. You reach it by working methodically through every competing explanation and finding that none of them, individually or in combination, account for what the data shows. The 99.7% figure that has appeared in coverage of this discovery is the complement of that number, not a claim pulled from optimism, but the residual confidence left standing after the full battery of non-biological models has been tested and found inadequate. What makes the combined signal especially striking is the scale it implies. Earth's atmospheric disequilibrium, the methane-oxygen tension, the continuous cycling of carbon and sulfur compounds, the persistent chemical anomalies that mark a living planet is the product of an entire global biosphere operating at full capacity. Every forest, every ocean surface, every gram of topsoil, every deep-sea hydrothermal vent community contributing its metabolic output to the cumulative disruption of equilibrium chemistry. The signal is real but diffuse, spread across a full planetary surface and ocean volume. Earth's biosignature dilutes to the point where detecting it from interstellar distances would require instruments more sensitive than anything currently in operation. K2-18b's atmospheric anomalies register at 4.2 sigma from 120 light-years away on an instrument with known, calibrated sensitivity limits. For that signal to reach that confidence level across that distance, the biological processes maintaining it, if biology is what is maintaining it, must be operating at a volumetric scale whose atmospheric output exceeds what Earth's biosphere produces in comparable terms. Not necessarily more complex, not necessarily more diverse, but producing enough metabolic byproduct, distributed widely enough across a planetary ocean, 8.6 times Earth's mass, to push atmospheric concentrations into ranges that Webb can read from across interstellar space. There is a quiet absurdity in that picture worth pausing on. K2-18b is, in one sense, behaving like a planetary-scale organism, its ocean exhaling chemistry upward through hundreds of kilometers of hydrogen atmosphere, the cumulative product of whatever is living in it, rising all the way to the spectroscopic layer that Webb reads when starlight filters through the planet's rim. We did not land on it. We did not send a probe. We did not travel a single kilometer toward it. We pointed a telescope at the light of its star and read the gaps in that light, and the gaps said the planet is not chemically empty. K2-18b is essentially breathing on a global scale, and we caught it doing exactly that from 120 light-years away. By looking at the light of its host star, and the way we caught it, that method, that mechanism, that piece of physics and engineering is the real miracle of this story. Pass sunlight through a prism, and you get a rainbow white light split into its component colors, red on one end, violet on the other. The full visible spectrum laid out in order of wavelength. Most people have seen this. Most people have moved on from it. But look more carefully at that rainbow, not the broad sweep of color, but the fine detail within it, and you notice something that most physics textbooks mention and most readers forget. The spectrum is not smooth. It is crossed by dark lines. Thin, precise, fixed lines sitting at specific positions across the color range. Not smudges or gradients, distinct, reproducible gaps in the light, appearing at exactly the same positions every time the experiment is run. Those dark lines are the spectral fingerprint of the elements inside the sun. Every element, every atom, every molecule absorbs light at specific wavelengths determined by its electron structure. When sunlight passes through the sun's outer atmosphere before reaching us, the atoms present there intercept photons at exactly the wavelengths they absorb and remove them from the beam. What arrives at Earth is sunlight with absences carved into it, a spectrum with gaps. The gaps don't appear randomly. They appear at the precise wavelengths corresponding to the elements doing the absorbing. Hydrogen leaves its lines, sodium leaves its lines, calcium leaves its own. each one different from every other, as individual as a voice in a room full of voices. Think of it as a concert hall where every instrument plays simultaneously. The combined sound is dense and complex, a wash of overlapping tones. But sit with a good enough set of ears, or a sensitive enough microphone and signal processor, and you can isolate individual instruments from the mix. The cello here, the oboe there, the French horn underneath. Every instrument has a characteristic timbre, a spectral signature in the sound domain that distinguishes it from every other instrument, even when all are playing together. The absorption spectrum of a star or planetary atmosphere works by exactly the same principle. Translated into light instead of sound, every molecule present leaves its characteristic gap in the spectrum. Given a detector sensitive enough to resolve them, you can read every molecule present in an atmosphere from its pattern of absences without being there, without touching it, without anything physical crossing the distance between you and the target. Webb's primary mirror spans 6.5 meters across gold-coated, each segment precisely aligned to function as a single collecting surface. Its infrared sensitivity is 100 times greater than the Hubble Space Telescope's. The development program ran for 25 years. The final cost reached $10 billion. It sits at the second Lagrange point, 1.5 million kilometers from Earth on the sun-facing side, in an orbital position chosen specifically to give it an unobstructed view of the sky with stable thermal conditions. $10 billion to smell the ocean of a planet 120 light years away. That sounds insane, until you understand what it found. The technique Webb used to read K218b's atmosphere is called transmission spectroscopy. The mechanics are precise and, once understood, genuinely difficult to describe as anything other than remarkable. When K218b passes in front of its host star, an event called a transit, occurring on a 33-day orbital period, a portion of the star's light doesn't travel directly to Webb through empty space. Some of it passes through the thin atmospheric annulus at the planet's edge, the narrow ring of gas at the planet's rim, where the atmosphere transitions from opaque interior to transparent space. That atmospheric layer intercepts photons at the specific wavelengths, corresponding to the molecules present within it. Those photons are absorbed. What continues toward Webb is starlight with a new set of absences, carved into it by K218b's atmospheric chemistry. Webb collects that light. It spectrographs NIR SPEC, the near-infrared spectrograph, and MIRI, the mid-infrared instrument, spread it across detectors covering wavelengths from roughly 0.6 micrometers out to 28 micrometers. The resulting spectrum is compared against the baseline stellar spectrum, measured when the planet is not transiting, when Webb is seeing the star's light without any planetary atmosphere in the way. The difference between the two spectra is the atmospheric signal the additional absences introduced by K218b's atmospheric molecules during transit. Dimethyl sulfide has strong absorption features at approximately 3.3 micrometers and 9.7 micrometers in the infrared. Methane absorbs at its own characteristic set of wavelengths, carbon dioxide at another, ammonia at another still. Each molecule leaves its own pattern of gaps. Webb reads them simultaneously across a detector range wide enough to capture multiple molecular fingerprints in a single observation. Think of it this way. Hold a cup of coffee up between your eye and a lamp across the room. The light reaching you is brown filtered through the coffee, carrying its color. If you had an instrument sensitive enough to analyze that filtered light in detail, you could read the chemical composition of the coffee caffeine content, sugar concentration, milk proteins without touching the cup, without tasting it, without any physical contact at all. The light would carry the information. Your detector would extract it. Webb is doing exactly that. Scaled to 1 trillion, 136 billion kilometers, the distance separating it from K218b, It is reading the chemical composition of a planetary atmosphere by analyzing what that atmosphere does to the starlight passing through it across a distance that makes the entire history of human exploration look like a short walk to the corner. The cup of coffee is an alien ocean world. The lamp is a red dwarf star. The detector is the most sensitive infrared spectrograph humanity has ever placed in space. And the readout contains the fingerprints of molecules that, on Earth, are only ever produced by living things. The Cambridge team did not run one transit observation and publish. Each transit event lasts roughly 2.5 hours. Multiple transits were observed across separate windows. The data accumulated and stacked to build signal against noise. 2 independent analysis teams worked from the same raw data set without sharing intermediate results. A blind analysis structure designed to prevent confirmation bias from shaping the outcome. Both teams, working separately, extracted the same molecular fingerprints from the spectrum. The signal did not depend on any single processing choice. It was present across multiple independent analytical approaches, stable across multiple observation epochs, resistant to every systematic error the teams could identify and model. 4.2 sigma, from 120 light-years, through the filtered light of a dim red star, by reading the gaps. That technique, that method of catching a planet in the act of having an atmosphere, of reading its chemistry from the shadows it casts in starlight, is beautiful in a way that feels almost disproportionate to the machinery producing it. The universe stores an enormous amount of information in light, and Webb was built to read it. The result is that a telescope floating 1.5 million kilometers from Earth can tell us what molecules are present in the atmosphere of a world we will never visit in any human lifetime, with a confidence level high enough to constitute the most significant potential discovery in the history of the search for life. But the technique and the numbers are only the instrument and its readout. What the readout forces us to confront what it does to the way we understand ourselves and our place in the story of the universe is the part that cuts deepest. A single transit observation of K2-18b lasts approximately 2.5 hours. That is how long the planet takes to cross the face of its host star from Webb's line of sight. 2.5 hours during which starlight filtered through the atmospheric rim arrives at the telescope, carrying the molecular fingerprints of whatever is present in that atmosphere. 2.5 hours of signal, collected once, produces a spectrum with a signal-to-noise ratio that, for a planet 120 light-years away around a dim red dwarf, is not sufficient on its own to make confident molecular identifications at the sigma levels this detection requires. So the Cambridge team did not rely on one transit. They observed many, across multiple observation windows spread over months. Each new transit adding signal to the accumulating data set. The team stacked the spectra mathematically, combining the light collected across separate events to build a composite signal that grows stronger with every addition, while the random noise, which varies independently from one observation to the next, averages down. The underlying molecular signatures, being real physical features of the atmosphere that reproduce consistently across every transit, grow more distinct with each observation added to the stack. The noise retreats. The signal emerges. The process is slow, methodical, and the only way transmission spectroscopy at interstellar distances works at all. The instruments doing the collecting are Webb's 2 primary spectrographic tools. NIR-SPEC, the near-infrared spectrograph, covers wavelengths from approximately 0.6 micrometers to 5.3 micrometers. MIRI, the mid-infrared instrument, extends that range out to 28 micrometers. Together, they give Webb continuous spectroscopic coverage across a wavelength range that encompasses the characteristic absorption features of virtually every molecule of astrobiological interest. Dimethyl sulfide absorbs strongly at approximately 3.3 micrometers and 9.7 micrometers. both within Webb's combined instrument range. Both detectable, given sufficient signal accumulation, methane, carbon dioxide, ammonia, water vapor all leave their fingerprints at wavelengths these instruments can resolve. The coverage was not accidental. Webb was specified to cover this range precisely because planetary atmosphere science required it. You might be thinking, at this point, that noise is still a concern. Instrument artifacts, systematic calibration errors, subtle biases introduced by the data reduction pipeline. Maybe the signal at 3.3 micrometers is real, but the one at 9.7 micrometers is an artifact of how the MIRI detector was calibrated on that particular observation run. Maybe the methane feature is genuine, but the carbon dioxide elevation is an artifact of a different systematic error. Maybe the whole picture looks coherent because the same processing bias is affecting multiple features simultaneously in a way that mimics a real atmospheric composition. The research team spent 18 months working through exactly those possibilities before publishing. The verification architecture the Cambridge group applied was not a single check. It was layered, designed to catch failure modes that a simpler approach would miss. The first layer was blind analysis. Two independent analysis teams, working from the same raw Webb data, were prohibited from sharing intermediate results until both had completed their independent reduction and spectral extraction. Each team made its own choices about data reduction steps, calibration corrections, and atmospheric retrieval methodology. When both teams unblinded their results, they had arrived at the same molecular detections from the same data set using different methods. The signal was not an artifact of any single processing choice. It survived two independent approaches applied without coordination. The second layer was atmospheric retrieval modeling. The retrieval codes used to interpret the spectrum don't fit a single model against the data they explore the full space of possible atmospheric compositions, running millions of model atmospheres that vary in temperature profile, molecular abundances, cloud coverage, and chemical mixing ratios. Each model generates a predicted spectrum. The code compares each predicted spectrum to the observed one and assigns it a probability based on how well it fits. The output is not a single answer, but a probability distribution across the full parameter space, a map of which atmospheric compositions are consistent with the data and which are not. The DMS detection, the methane and carbon dioxide elevations, the ammonia deficit all emerged from this full probabilistic exploration of the atmospheric parameter space, not from fitting a predetermined model to the data. The third layer was peer review by 6 independent reviewers, each assessing the methodology, the data quality, the retrieval framework, and the statistical claims before the paper reached publication. 6 reviewers is not standard for a routine astronomical result. It reflects the magnitude of what the paper was claiming and the corresponding standard of scrutiny the authors and journal editors agreed the claim required. 18 months, 2 blind analysis teams, millions of model atmospheres, 6 independent reviewers. The signal survived all of it. Webb was designed with a minimum operational lifetime of 10 years and carries fuel sufficient for approximately 20 years of operation. K218b will be observed again not once more, but dozens of additional times across Webb's operational life, each observation adding to the accumulated transit data set, each addition pushing the sigma level of every molecular detection incrementally higher. The path to 5 sigma, the threshold that physics and astronomy have established as the standard for a confirmed detection, is not a distant aspiration. It is a calculation. Given the current 4.2 sigma baseline and the number of additional transits Webb can realistically accumulate before its fuel runs out, 5 sigma on the DMS detection is achievable within the telescope's operational lifespan under conservative assumptions about observation scheduling. The 5 sigma standard exists because the scientific community learned, through painful historical experience, that confident detections below that threshold have a non-trivial rate of evaporating under subsequent scrutiny. The graveyard of 3 sigma results in particle physics and astrophysics is well populated. 5 sigma was chosen specifically because at that confidence level, the rate of false positives drops to a frequency that the community decided was acceptable for making formal claims. It is not a threshold chosen arbitrarily. It is a threshold chosen because the community knows how badly it wants some results to be true and built a standard high enough to protect against that wanting. The scientists who set 5 sigma as the discovery threshold did so, knowing full well that any result approaching it would send the global scientific community and everyone watching into a state of controlled frenzy. And everyone is already there at 4.2 sigma, completely, understandably, justifiably there. The standard exists precisely because this kind of claim demands it, and the process working toward it is already in motion. The numbers will keep improving, the transits will keep coming, the data set will keep growing, and at some point, the sigma level will cross 5, and what is currently the strongest biosignature candidate in the history of the search will become, by physics standards, a confirmed detection. But sigma levels are statistics. The thing that actually moves the thing that cannot wait for 5 sigma to begin its work is not the data itself. What genuinely shakes you is what the data forces you to reconsider. For the entire span of recorded human history, from the first scratched symbols on cave walls to the present moment, people have looked up at the night sky and asked the same question. Are we alone? The words change across languages and centuries. The question does not. It appears in ancient cosmologies, in religious traditions on every inhabited continent, in philosophy from the pre-Socratics to the present, in the popular imagination of every culture that has ever spent a clear night outside, staring upward. It is not a scientific question at its root. It is something older and more fundamental. A composite of philosophy and fear and hope wound so tightly together that separating the strands is impossible. We want an answer. We are also in some quiet part of the mind that doesn't admit this easily, afraid of what either answer means. Every major scientific revolution since Copernicus has answered a different version of that question by making humanity smaller, not diminished in worth, but smaller in scope, more precisely located within a larger frame. Copernicus moved Earth from the center of the cosmos to one planet among others, orbiting an ordinary star. The universe did not revolve around us. We revolved within it. Darwin moved humanity from a specially created species to one branch of an evolutionary tree that connects every living organism on the planet through 4 billion years of common ancestry. We were not designed. We were selected for, from the same raw material as everything else alive. Each revolution required the same psychological adjustment, giving up a position of special centrality and constructing a new understanding of significance that didn't depend on being at the center. Neither revolution diminished what it means to be alive or human. Both made the picture more honest. Both required rebuilding something that felt, before the revision, like solid ground. If K218b confirms life, if the 4.2 sigma detection crosses the 5 sigma threshold, and the Cambridge team's interpretation survives the full battery of subsequent scrutiny, the revision required will be of a different character than Copernicus or Darwin, but structurally identical in what it demands. For the first time in human history, we would hold empirical evidence that life is not an accident specific to one planet, not a philosophical argument, not a statistical inference, actual observational data, extracted from starlight, demonstrating that the chemistry of living processes has appeared independently in at least 2 locations in the universe, locations so different from each other in composition, stellar environment, planetary structure, and atmospheric chemistry, that the only thread connecting them is biology itself. That is not a refinement of the existing picture. That is a phase transition in how the universe is understood. If life arose on Earth under one set of conditions, and on K2-18b under a radically different set of conditions, the logical inference is that the origin of life does not require a specific and narrow set of prerequisites. It requires conditions broadly favorable to chemistry, energy gradients, and molecular complexity. And those conditions can be satisfied in ways we are only beginning to enumerate. Life, in that interpretation, is not a cosmic accident. It is something closer to a chemical inevitability, a process that emerges wherever the conditions permit it to, across a range of planetary environments, far wider than any previous framework assumed. If life emerged in two places that look this different from each other, how many places haven't we looked at yet? That question does not have a comfortable upper bound. The observable universe contains an estimated 2 trillion galaxies. The Milky Way alone holds somewhere between 100 billion and 400 billion stars. A substantial fraction of those stars host planetary systems. If even a small percentage of those planets meet the conditions for biology conditions that K2-18b is demonstrating are far less restrictive than previously believed. The number of worlds currently hosting living processes is not dozens or hundreds. It is, by any reasonable extrapolation, millions, possibly far more. The Drake equation has a term for this. F sub L, the fraction of planets with suitable conditions where life actually emerges. In the decades since Frank Drake first proposed the equation in 1961, that term has been the most uncertain variable in the calculation. Estimates have ranged from near 0 to near 1, with no empirical anchor to constrain them. A single confirmed independent origin of life, a second genesis, anywhere in the universe. Under any conditions changes F sub L from an unbounded philosophical guess to a quantity with at least 2 data points. 2 data points is not a large sample, but it is infinitely more informative than 1. And if the distribution of planetary conditions required for life includes Hycean worlds, which may account for 35 to 40% of super-Earth's inhabitable zones, the eligible planet population that F sub L applies to expands by orders of magnitude. The Milky Way, on those revised assumptions, may contain not thousands, but millions of worlds where living processes are currently underway. That conclusion should feel like an answer to the question humanity has been asking since before writing existed. It is the closest thing to a yes that physics and astronomy have ever produced. But it doesn't feel like an answer. It feels like the opening move in a much harder problem. Because if life is that common, if the galaxy is genuinely populated with worlds where biology is running, then the universe should be full of signals, full of evidence. Chemistry is not the only thing living systems produce. Complex life produces behavior. Behavior, at sufficient technological development, produces emissions radio waves, structured light, atmospheric pollution from industrial processes, signatures of large-scale energy use. A galaxy containing millions of inhabited worlds should, if any significant fraction of those worlds developed technological civilizations, be leaking detectable signals in every direction. The universe is not leaking signals. It is silent, life widespread, but the universe silent. That is the most terrifying contradiction K2-18b puts on the table. K2-18b carries a 4.2 sigma biosignature. It does not carry a radio signal. The SETI Institute has been monitoring the radio frequency spectrum from the direction of K2-18 for years. The frequency range searched spans the bands most commonly proposed as candidates for intentional interstellar communication: hydrogen line frequencies, water hole frequencies, structured pulse patterns, anything that bears the statistical signature of artificial origin rather than natural astrophysical processes. The result? Across every observation run conducted on K2-18 is silence. No radio emissions, no laser pulses, no structured light signals, no atmospheric chemistry, consistent with large-scale industrial processes, layered on top of the biosignature molecules Webb detected. Nothing that suggests a civilization is present, has ever been present, or is attempting to communicate from that system in any way detectable by current instruments. That silence is not a failure of the detection. It is, in fact, a data point of its own, and it points somewhere specific. The most straightforward interpretation of a strong biosignature, combined with a complete absence of technological signatures, is that whatever is producing the DMS and maintaining the atmospheric disequilibrium on K2-18b has not developed technology, single-celled organisms, microbial mats, simple multicellular life operating at the level of basic metabolic chemistry, consuming nutrients, releasing byproducts, filling a planetary ocean with the chemical exhaust of biological processes, entirely unaware that a telescope 120 light-years away is reading their existence in filtered starlight. Life at the level Earth reached somewhere between 3.5 and 4 billion years ago, before anything with a nervous system existed, before anything capable of sensing the scale of its own world had yet evolved. That picture is entirely consistent with what Webb has detected. The biosignature molecules are metabolic byproducts, the output of biological chemistry, not the output of technology. Technology leaves different marks. Industrial chemistry alters atmospheric composition in ways that differ from biological metabolism. Electrical generation produces radio frequency emissions. None of those marks are present. What is present is precisely what microbial life in a planetary ocean would produce, at exactly the scale a planetary-scale biosphere would produce it, which raises a question that cuts deeper than the detection itself. If marine microbes are the most common form of life the universe produces, if the typical endpoint of billions of years of biological evolution across the galaxy is a planetary ocean full of single-celled organisms metabolizing quietly and going nowhere in particular, what does that say about us? Two scenarios follow from that question, and they point in opposite directions with equal force. The first intelligence is a genuine rarity. Life emerges readily. K2-18b suggests the chemistry of abiogenesis is not the bottleneck, but the transition from microbial life to complex multicellular organisms, from complex organisms to nervous systems, from nervous systems to self-awareness and technology. Each of those steps may be improbable in ways that keep most living worlds permanently at the microbial stage. On that reading, a galaxy full of ocean worlds hosting bacterial ecosystems and nothing more would leave the development of technological intelligence as an extraordinarily rare event. Perhaps it has happened only once in the Milky Way, perhaps a handful of times. Perhaps Earth is, in the truest sense, exceptional, not in having life, which may be common, but in having produced a species capable of building a telescope to look for it. That exceptionality, if real, confers both extraordinary value and extraordinary responsibility. The rarity is not a reason for comfort, it is a reason for care. The second scenario is darker. Intelligence may not be rare at all. It may be a predictable outcome of sufficiently long evolution under stable conditions, which red dwarf systems provide in abundance. But technological civilizations, once they develop, may carry within their own complexity the seeds of their destruction. Resource exhaustion, self-inflicted environmental collapse, the development of technologies whose destructive potential outpaces the wisdom required to manage them. A civilization advanced enough to produce detectable signals might, by the same logic, be advanced enough to eliminate itself before those signals have traveled far enough to reach anyone. On that reading, the silence is not absence, it is aftermath. The galaxy may be full of worlds that had civilizations, and the reason we hear nothing is that civilizations are self-terminating processes on timescales shorter than interstellar detection requires. Both scenarios are currently consistent with the available evidence. Neither can be ruled out. The silence from K2-18b does not distinguish between them. It is consistent with pre-technological life, which the first scenario predicts, and would also be consistent with a civilization that burned itself out before developing the kind of persistent, long-range emissions that SETI searches for. The data doesn't resolve the fork. It just makes the fork unavoidable. After centuries of worrying that we might be alone in the universe, it turns out we may face the opposite anxiety, that our cosmic neighbors are vast oceans of algae who have no idea we exist and are getting along perfectly fine without that knowledge. There is something genuinely funny about that picture, until you sit with it long enough for the humor to curdle into something more uncomfortable. The company we've been hoping for? The contact, the communication, the sense of not being the only mind in a universe this large may simply not be there, not because life is absent, but because life has no particular tendency to become minds. It fills oceans, it saturates atmospheres with its chemical byproducts. It runs for billions of years on the energy of a patient red dwarf star, metabolizing and reproducing and doing everything biology does, without ever producing a single thought about the stars above it. But even microbial life on K2-18b, even the most chemically simple, cognitively absent, biologically unremarkable single-celled organism floating in that hydrogen-covered ocean would carry implications that dwarf every other discovery in the history of science. Because its existence would prove, with the force of a second data point, that abiogenesis is not a miracle, not a 1 in 10 to the 40th power statistical accident that happened once in the history of the universe and gave rise to everything living on Earth by a cosmic stroke of luck. Abiogenesis, the emergence of self-replicating chemistry from non-living molecular systems, would be demonstrated to be a process that happens under the right conditions, repeatedly, reliably, perhaps inevitably. The transition from chemistry to biology would join gravity and thermodynamics in the category of things the universe does, because the underlying physics makes it happen, not because something extraordinary intervened. That reclassification is not a small adjustment. It is the removal of the last philosophical firebreak between life as a special phenomenon and life as a natural one. Every framework that treats the origin of life as requiring special explanation, divine intervention, panspermia from some primordial source, a unique set of Earth-specific conditions never replicated elsewhere, collapses the moment a second independent genesis is confirmed. The argument from rarity evaporates. What remains is a universe in which chemistry, given time and appropriate conditions, becomes biology, routinely. And if life is that common, the question is no longer whether we are alone. The question is something deeper and considerably more frightening. If life is a natural law, not a miracle, not an accident, not a statistical outlier requiring special explanation, but a process as fundamental and reliable as gravity or the second law of thermodynamics, then the question changes. It stops being about presence or absence. It becomes something stranger and more unsettling. Why does the universe produce life at all is the universe, in some sense that physics has not yet found a way to formalize, oriented toward it. That question sits at the boundary between science and philosophy, and it has two serious answers that have been in tension for decades. The first is the anthropic principle. In its various formulations, the anthropic principle holds that the universe appears fine-tuned for life, because only in a universe capable of producing observers can observers exist to notice the tuning. We find ourselves in a universe where the constants permit life, not because the constants were designed that way, but because we could not be asking the question from any other kind of universe. The fine-tuning is real, the argument goes, but it requires no explanation beyond the selection effect of our own existence. It is, at its core, a statement about what we can observe, not about what the universe intended. The second is what some cosmologists and philosophers call cosmic biology, the view that the universe's physical constants are not merely compatible with life, but structured in a way that makes life's emergence inevitable, given sufficient time and appropriate conditions, not designed by a mind, not the product of intention in any theological sense, but oriented in the sense that a river is oriented downhill, not choosing to go there, but going there because that is where the physics leads. The backdrop for both arguments is the same set of facts, and those facts are genuinely difficult to dismiss as coincidence. 20 fundamental physical constants underlie the structure of the universe as we know it: the gravitational constant, the mass of the electron, the speed of light, the strong nuclear force coupling constant, the cosmological constant governing the expansion rate of space itself. Each of these values falls within a range in most cases, an extraordinarily narrow range that permits the existence of stars, the fusion of carbon in stellar cores, the formation of planetary systems, the chemistry of organic molecules. Adjust the gravitational constant upward by a few percent, and stars collapse before igniting sustained fusion. Adjust the strong nuclear force slightly, and carbon cannot form in stellar interiors, eliminating the chemical backbone of every known form of life. Adjust the cosmological constant by a factor that sounds modest, and the universe either collapses back on itself before galaxies form or expands so rapidly that matter never coalesces into anything at all. 20 constants, all sitting in the narrow ranges that permit complexity, chemistry, and biology, not one of them, as far as current physics can determine, required by any deeper principle to have the values they have. They are, as the data stands, contingent. They could, in principle, have been different. And if any of them had been different by margins that sound small in absolute terms, the universe would contain no stars, no carbon, no planets, and no one asking any questions. The universe is 13.8 billion years old. Life appeared on Earth within the first billion years after the planet formed as early as the conditions permitted. The strongest candidate for life beyond Earth orbits a star that may be older than our solar system, suggesting life appeared there early in that system's history as well. Life emerges as soon as conditions allow. It emerges in environments radically different from each other. It fills whatever ocean it finds itself in and saturates whatever atmosphere sits above it with the chemistry of its own processes. Is this still coincidence? That question has no scientific answer yet. The anthropic principle offers an explanation that requires no mechanism beyond selection bias. Cosmic biology suggests a universe whose physics systematically favors the emergence of complexity. Neither position can be empirically tested against the other with current tools. The honest answer is that we don't know which framework, if either, is correct. What K2-18b contributes to that debate is not a resolution, it is a data point. A second confirmed inhabited world, if confirmation comes, does not prove that the universe intended life, but it shifts the empirical ground under the discussion. Every additional world where life has independently arisen is another data point on the distribution. 2 data points define a line, however tentatively. Enough data points, drawn from enough different planetary environments across enough different stellar systems, begin to trace the shape of something that looks less like coincidence and more like a pattern. A pattern in the data is not proof of intention, but it is the kind of thing that demands an explanation, and the explanations available range from the purely statistical to the philosophically profound. Asipalmamais 218be is not just a planet with a possible biosignature. It is a data point in the map of what the universe does with itself across 13.8 billion years of available time. Each world confirmed to carry life adds to that map. Each addition makes the question of whether the universe is neutral toward life indifferent. running its physics without any particular tendency to produce biology harder to maintain against the evidence. The universe may not be neutral. It may, in whatever sense physics can eventually formalize, be the kind of place that makes life wherever it can. Maybe the question, "Are we alone?" was the wrong question from the beginning. Maybe the right question is, have we been looking widely enough? We spent decades searching for a second Earth. What we found instead is an ocean world 8.6 times our mass, wrapped in hydrogen, orbiting a star that will outlive every sun-like star in the galaxy, carrying the chemical signatures of living processes readable from 120 light-years away. Nothing about it fits the template we built. Everything about it suggests the template was too small. The James Webb Space Telescope has opened a door. Behind that door is not an answer. Behind it is something far richer and far more unsettling, a cascade of deeper questions, more beautiful and more frightening than anything we thought to ask before the door existed. Pull back from everything: the numbers, the molecules, the instruments, the distances that reduce human experience to irrelevance. Set all of it down for a moment and look at the shape of what this story actually is. It started with a smell, the specific, unremarkable, slightly pungent smell of the ocean. The thing you notice for 30 seconds when you step onto a beach and then stop noticing entirely. A metabolic byproduct of microbes eating lunch, exhaled into the air by organisms so small they have no awareness of existing. That smell has a name. That name has a chemical structure. That chemical structure has a spectroscopic fingerprint. And that fingerprint showed up in the light of a star 120 light-years away, filtered through the atmosphere of a world nothing like ours, read by a gold-coated mirror, floating alone in the dark between Earth and the sun. From a beach smell to a question about the nature of existence, that is the actual distance this story traveled. 4.2 sigma is the most beautiful and most frightening number in the history of astronomy. Beautiful because it is close enough to touch 99.7% is not a rumor or a hope. It is the residual of an exhaustive elimination process run by some of the most careful scientists working today. Frightening because the remaining 0.3% still exists. The signal could, by the mathematics, still be an artifact, an uncharacterized systematic error, something exotic and abiotic that no current model accounts for. We do not yet know. And that not knowing, that specific, charged, almost unbearable suspension between the most significant yes in human history and the possibility of a very expensive no, is the most honest place science has ever stood on this question. The best models of Hycean worlds are built on one example. Webb needs more transits, more data, more years of patient accumulation before the sigma level crosses the threshold physics requires. Our understanding of hydrogen ocean chemistry is incomplete in ways that will take decades to address fully. The conclusion that feels so close is not yet in hand. We are at the edge of the answer, not past it. Standing at the edge of understanding is not a failure. It is the most productive location a species can occupy. Every discovery that changed the human picture of the universe began with someone standing exactly there at the boundary between what was known and what wasn't, deciding to look one more time. K2-18b is out there right now, 120 light-years away. Its ocean moving in whatever currents a hydrogen-covered global sea generates. Its atmosphere cycling through whatever chemical processes are maintaining. That persistent, inexplicable disequilibrium, whether anything in that ocean is alive or not. The planet doesn't know we're watching. It doesn't know we exist. It is simply doing what it does, breathing, if that is what it's doing, at planetary scale. Indifferent to the telescope, we pointed at its star. The only question left is this: when the answer finally comes, when the sigma crosses 5 and the detection is confirmed, or when subsequent data unravels, will we be ready for what it changes?